All right, thanks for the introduction. Welcome to this presentation. Although it's marked as ninja style, this is really introductory style. So don't be scared. Try to explain you how the USB basics, how USB protocol works, and how to use usbmon to check an unknown device. Yeah. My name is Klaus Kämpf. I'm with SUSE for almost 13 years now. I started with Just, doing systems management, and I still do a lot of systems management. I'm now a project manager, and the good thing about working at SUSE is you get hack weeks. This is 2 times a year, 1 week of free hacking, whatever you want. And what I'm presenting today, this is actually my story about the last hack week, about hack week 8, what I did there. So, you're probably here because you have some crazy, unknown, or even a dangerous USB device, and you're curious how to code a Linux driver for this, or how it actually works on the USB level. So my crazy device was this beast. It is a slide scanner. You can scan multiple slides. And I see a couple of young geeks here, so I think a bit of explanation is due. What is a slide? This. So actually it's this size. It was used to take photos back in the last millennium. And to view these things, you needed a projector with a lamp, like in a cinema. And the good thing is, what very bright colors. You had backlight, like you use now with all your laptops and iPads and whatnot. And usually when you started with this, you took a lot of pictures, and I'm being a lazy guy. I never really sorted them. I got them in this nice slide package, and then I kept it in these things. And usually you have plenty of those, very, very many. And they are back in the cellar, and viewing them is kind of cumbersome. You need something like a bright white pane, and the projector, you put it out and then you go through them, and very, very cumbersome. So my goal really was to have them digitized and be able to view them in the computer and to tag them and to organize them, but that's a different story. And actually for these slides there are many slide scanners available. But a lot of them only do single slides. Or you have kind of flatbed scanners where you put the slides on top with a backlight, and you have to put all the slides out and put them on the slide scanner or into the single slide scanner. And this is why I got myself this big beast, but of course only with a Windows driver. So, but there is some hope in the Linux world, and this is called the SANE, or SANE project, and this stands for Scanner Access Now Easy. And this is a rather big project doing scanner drivers for all kinds of scanners since years. They have a rather big database of scanners, so if you go to this web URL, you can search for your scanner and find out about it and about the driver state, if it's fully supported or unsupported. But there was not much about my scanners. So what did I do? Of course, I started with Google. And that's the first word of my presentation title. So I Googled for the scanner, I Googled for the vendor, I Googled for any information. I even disassembled it, looked at the hardware, identified the chips, and then I Googled for all the chips, which sometimes is helpful because a lot of scanners have similar chips, but all I got was unsupported, unknown. Couple of questions. Hey, does a Linux driver exist? So, yeah. But actually, Google revealed a couple of things which proved to be helpful, and this was the original equipment manufacturer. So the company I bought it from in Germany just repackaged it, put their own label on it, but originally it comes from Pacific Image Electronics, which is a rather large vendor of all kinds of scanners. And that was, in the end, a very good thing. I have a web page there, and they have lots of different scanners, different interfaces, parallels, SCSI, Firewire, USB, and whatnot. And what you should keep in mind if you have some crazy unknown USB device, that OEMs move very, very slowly. So they usually get some new device, some new feature in it, some new packaging, and so on. But the internals change very, very slowly. And we will see later where this has an effect. But it proved to be very helpful in order to understand the protocol. And if you have some crazy unknown USB device, go look for similar devices which do similar things. Go look for the original equipment manufacturer. Open the device, look at the chips, and so on, and you will find a lot of similarity across the devices. But yeah, it didn't really help me to reach my goal. It was only small steps. So I started with reverse engineering. And that was looking at the actual USB protocol. So how do you do this if you only have a Windows driver? There are a couple of USB protocol analyzers, protocol sniffers available in Windows. But being a Linux geek, that's not how I wanted to work. I wanted to have normal Linux text files and then use normal Linux operations. And I want to have a Linux driver, not a Windows driver. So in order to find out what the Windows driver did, I used this combination. And this proved to be very, very good. I tried it with KVM, of course. The problem with KVM is the USB 2.0 stack. I couldn't get it to work, especially with Windows. VirtualBox, it's free, it's available for OpenSUSE. Wonderful, it has a decent USB stack. You only need these extension packs and the driver ISO. It's all free. You can download at virtualbox.org. I had an old copy of Windows XP. I put it on this, and my scanner worked with an virtualized Windows. So it was great. And then I started to look, okay, what kind of tools are there in the Linux world? And there is usbmon. So how many of you have heard about usbmon already? Raise your hand. So not very many. Good. Then for the rest of you, I have something to tell. So usbmon is a kernel module which intercepts the USB stack and puts it out as text file. And it's a very, very raw dump of the USB traffic. So how do you use it? Actually, you need to be root to install the module, and then a new directory exists under syskernel debug USB usbmon. And this has these crazy file names in it. And once you see these names, then you know, okay, usbmon has been loaded and I am ready to use it. So what you need then is an ls USB, and you need to know where is my device I just plugged in. And what you actually need is the vendor and the product ID, because this shows you, okay, this is your device. You can also do, I think it's ls USB-v, which then shows you an explanation, a name, puts a name to this vendor code. But the most interesting for you is usbmon is the bus number. This is what you really need. And then you can do sniffing the protocol like this. Very simple, very basic command line stuff. And what you get then is something like this. Does it look scary? It scared me a lot. So I didn't really know what it is and how I would ever make heads or tails out of this. And But the nice thing about the USB, there are open specs, there are a lot of documentation, so you can find everything on the internet, or you can visit the OpenSUSE conference and listen to my talk, because I'm going to explain it to you now. USB basics. So what is USB? So USB is the universal serial bus. And the topologically, it looks like this. It's star-like. So on top you have your host system, and you can connect multiple devices to this. And a typical device, for example, is a hub. Everyone should know what a USB hub is. It just has one input port, and then you can connect multiple devices. And typical use case for a hub is not only to give you more USB ports, but also to give power to these USB ports, because usually on USB you also distribute power this way. And then the endpoint is usually device. So a toaster, maybe, USB disk, a stick, or something like that, or a scanner. And inside the device, this is why there's a frame around this toaster, there are so-called endpoints. And USB works this way, that it creates so-called pipes, so the host can only talk to one endpoint at a time. It's usually short kind of bursts which go, and then it talks to the next device or endpoint. So all the devices, they compete on this bus, because up there the host usually only has 1 or 2 or 3 USB ports, and all the devices on one port compete on bandwidth and on power. So when you plug in a device, the host and the device begin talking. The host queries the device, hey, who are you? What do you need? What kind of bandwidth do you need? What kind of USB device are you? And so there are a couple of parameters which the host queries. The first is the class of device. So what kind of device is it? Is it a keyboard? Is it a camera? Is it a USB stick? A scanner, and so on. And then a bit about details. So the vendor, the device number, and the model. This is then interesting for the driver. So what driver should be used for this device? Then they negotiate on the bus. address. So every time you plug in a USB device, a new bus address is negotiated. And if you watch warlock messages, if you unplug and plug a device, you see that it always gets a new address. Then, of course, bandwidth needs. So, for example, a streaming video device needs much more bandwidth than a keyboard. And power requirements. So now let's look at USB communication. And there are 4 modes of communication between host and the device. The first one is called control. These are actually normally commands sent to the device. So typically I want to write to this register or to this spot in the device. I want to send this command to the device. Or an inquiry from the host, give me the value of this register location, give me the status of the last command, something like this. So very small bursts, usually of 1 or 2 bytes between host and device. The next mode of operation is called bulk. And these are large data sets. So usually communication between a USB stick or an external disk device and the host. Or transferring from a scanner the scanned image in big chunks like 1 kilobyte, 4 kilobytes, whatever. Bulk transfer usually use whatever bandwidth is available, but they don't have a guaranteed bandwidth. So they just use whatever is there. But you don't know how much is it, so it means that there's also no guarantee how long the transfer will take. But for normal file transfer, all you want to ensure is that the file actually reaches your host or gets written to the USB device, and if it takes 2 seconds or 3 seconds, you really don't care. So the third mode is interrupt, and this means a bounded latency. And typical use for this is a keyboard or a mouse. So if you move the mouse, you immediately want the mouse pointer to move. And if there's a disk transfer happening in between, you don't want to move to have the mouse cursor wait for this. So interrupt really is what it says. It interrupts the current transfer, get the data to the host or to the device, and then the old transfer continues. And the last one is called isochronous. And this has a guaranteed data rate. Think about video or audio devices here, where you really need a fixed bandwidth in order to get the data across. Questions so far? All right. So, next. What is usbmon telling us in this data dump? And actually, it's not that complicated. So let me give you a small snippet of the usbmon output. Looks like this. This writes a single byte to the device. And what you see here is 2 lines, because the host writes the byte to the device, and the device acknowledges it. And this is true for all kinds of USB communication. So, in detail, The first column is the USB request block. This is an in-kernel memory address. It's useful for debugging USB stuff on Linux, but it wasn't completely useless for virtualized Windows via VirtualBox going through the kernel. The next column is very useful. This is a timestamp in microseconds. And this tells you where delays occur or where the driver waits. Especially in my scanner, if I issue USB commands too often, the scanner just locks up. So checking the delays the Windows driver puts in is showed up to be very, very important. Then the event type. So what you see here, it is, S stands for submission, so something the host sends to the device, and C stands for callback, so kind of acknowledge. And the third value here would be E for error. But so don't get confused. S is just the initiator. It could also be the device sending something to the host. Then this is the so-called address. And what we see here is a C for the type of communication. And we had these 4 types, control, bulk, and so on. And this is a control, and O stands for output. The next, after the colon, is the bus number. Then the device number on the bus and the endpoint. And more about endpoints later. And you see the acknowledge just repeats this. Then the so-called status. So S is for a so-called setup command. So the host writes a byte to the device. And the acknowledge here, the 0 is the acknowledge status, 0 meaning no error. And this is a setup package. So also actually quite easy. The 40 is a bit mask explaining the direction of communication. So 40 means the host sends something to the device. Then the next is the request. This is actually a command. So OC means write, apparently. That's what I got from the protocol. Then the next one is the value, which appeared to be the kind of register address. Then there's an index, which is unused. And I haven't yet found out why there's value and index. So seems to be 2 modes of addressing. Sorry? So it refers to port numbers. Okay, thank you. And then there's the length. So how many bytes are written? And in this case, it's just 1 byte. And then this was the kind of USB protocol, and then usbmon again repeats the 1 length in decimal. The first one was hexadecimal. Then an equal sign, and then comes data. In this case, it's 1 byte, could as well be multiple bytes. And the acknowledge is, okay, I received 1 byte successfully. So now I know what kind of data is written from the host to the device. And now we can look at more usbmon output. So I'd rather have a laser pointer here, but I don't. So what you can see a lot of in the third column, a lot of S and C. So host is sending setup commands to the device, and the device is acknowledging it. And then you see COs. This is a write to the device. CIs. This is the host requesting back from the device. Then you see BI. This is the bulk input. So there's some data transfer happening, and what you see on the first line is this 512 at the end. This means, okay, I have a 512 byte buffer. It's a read request to a 512 byte buffer, and the device replies with 12 bytes. What else can we see here? Yeah, the endpoint changes. So all the CI and COs, this is the last value after the third colon. The bulk input-output goes to a different endpoint. So this is here a typical use case for an endpoint. There's one endpoint for the commands and one endpoint for the data. Yeah. And that's about it. So, okay, now I have a rough understanding what is going on the USB bus, but really helpful for writing a driver? No. So the next tool I used, grep. Simple grep. Look what is going on. What kind of values are how often. I really used then typical tools like SAD, awk, cut is useful if you want to have specific columns, and spent like half a day just to make statistics. What kind of commands, what kind of values are used most, and pretty interesting was also, okay, I've then after some time saw, okay, there's a sequence of bytes repeating. So what is this? So I even wrote a tool to kind of capture these sequences and try to find out, okay, what is going on there. And this was quite helpful. And for example, this is a typical sequence. So look at the data bytes out there. So FF, AA, 5500, FF, 8778. This was a repeated sequence. So there must be something. And again, grep to the rescue. I checked out the SANE source code and grepped for these bytes. And what I found, for example, was the umax pp low, which had this line. And in the source code, I found this. And wonderful. AA 5500 FF 8778. Hooray! Wonderful. There's something. The problem is here, umax pp is for parallel port. I had a USB scanner, parallel port. Crazy. Crazy. Yeah. But, so, look here. All these bytes repeat here. And the interesting, after the 7.8, there is a command. So going back to the actual scanner protocol. So now I knew this E0 there is a command. Great. I had something I could search for in this driver. And then you can see the value. It's all 88 except the 2 bytes after E0. They go to 87. So it's also something different. And I found another driver of a HP, which had the similar sequence of 778, and then some IEEE 1284. Yes, this is parallel port. And what they do here is kind of sending a strobe signal to the parallel port. And this is, as I said before, OEMs move slowly. So it is a parallel port protocol on USB. Yeah, wonderful. Wonderful. So next step was all these hex dumps and so on. Okay, now I knew the basic sequence. So, I mean, being a geek and a hacker, I went hacking. Not a driver, but a protocol interpreter. And you can find it here. This is the result. This has a small scanner for the usbmon output to get the usbmon basics, and on top an interpreter for what I found out about the protocol. And what it does, it gives me this kind of output. So I have the timestamp here, and then a short notation of bus device and endpoint, and then what it is a setup command going from vendor, it's called in USB, which actually the host, to the device. The request type is C, so we now know this is a write command. The value, index, length, and the bytes, and then an ASCII representation of the bytes, which proved to be useful, for example, to see at one point the scanner response had the scanner name on it. So I knew somewhere before was kind of a inquiry command. Hey, who are you? So it narrowed it very, very much down. And what I also found out by reading through the source code of other scanners from SANE backend is the command is a SCSI command. So now we have everything. We have USB, parallel port, and SCSI. And what it actually is a parallel port basic protocol, so writing bytes, they used to transfer SCSI commands, and this all wrapped in USB. Wonderful. Yeah, so what I then wrote on top of this was, I called this digitdir because this is the name of my scanner. A more sophisticated interpreter of all these different layers. And what I did is I added code to distinguish these layers and to debug the various layers. So this is an output of D9, so full debug. What I have now done there is the time difference. And you can see here, for example, there's one command which is issued 171 milliseconds after the last. So the driver puts in a delay here. Then T plus, so overall time passed since start. And then which layer? It's a SCSI layer, it's a USB layer. So control bytes going there. And since now I knew it was SCSI, I could interpret the command values and get step by step to the core of the protocol. And if I run it with very, very little debug output, I see a scanner, the SCSI basics. So there is a test ready, which is often used. So just scanner, are you ready for the next command? Then it reads status, which is a more elaborate response. And then, for example, a write command setting the exposure time. So just like a camera with different exposure value, a scanner works just the same. Yeah. And based on this, I was able to write a driver. It was quite a success. And luckily, I also found other people interested in the driver. So, my result from Hack Week was I had a scanner protocol interpreter. I now can read the scanner protocol. I know everything about. And since I found others, because they were asking before on the mailing list and so on about these scanners, I contacted them, and now we are 3 people working on this, and the status today is we have a driver. And we discussed on SANE Devil and tried to improve it. My scanner is not fully working yet because I simply don't have time. It's just little timing issues which I still have to resolve. So, more questions? Then a summary. So, for all of you who have unsupported USB devices, yeah. Did I try running it to Wireshark? No. So I didn't know that Wireshark. How would, I mean, Wireshark probably would give me something like this. Yeah. Okay, no, didn't know. Yeah, but it's good advice. So does Wireshark use usbmon? Yeah. So I had similar tools found similar tools for Windows, but of course they are on this level. They show me the kind of USB basics, but not the different layers like this. So is it parallel? Yeah. Oh, the real breakthrough was seeing the different layers, that this is parallel port stuff, this is kind of introduction sequence. So going back here, all this FFAA55, this is a couple of bytes just to prepare the device for the SCSI command. Why? I don't know, but a lot of scanner use this. No idea. So, and what my tool does is just throws it away because this is repeated stuff. So my advice to you guys trying to write a USB driver or disassembling, so Google for information. There's a lot out there. Disassemble the device. Grab a screwdriver, whatever, look inside, look at the chips. Typically, chips are used in many devices and they give you some hints. If you have only a Windows driver, VirtualBox is really good. Had absolutely no problem with the USB stick, so this is actually very, very helpful. And I still work with this, so I do some like a pre-scan with the normal Windows software, do the usbmon trace, and then see or change the exposure time, switch from color to black and white, and then look, okay, what does it do on the protocol level? And yeah, to get this fully supported, it is a tedious task. You need to go to the windows, do some like shrink the scan area, scan it, then make it a bit larger, scan it, and then compare the usbmon debug output. What kind of values changed and where? The good old Linux tools, everything is a text file. They prove to be very, very helpful here to dissect all these hex dump bytes. And then go hacking. Go hack the device, write your own protocol interpreter, write a driver, and go out to the internet. There are plenty of other guys having similar interest. And of course, in a good old SUSE tradition, have a lot of fun. Thank you.